Welcome back, everyone. Today, we're starting a brand new Unity 2D series where we build a full Survivors.io style game completely from scratch. Movement, weapons, upgrades, enemies, everything. Step by step, clean and professional. Let's start by creating a new Unity project. Choose Unity 2D Core to keep things lightweight and optimized. I'm naming the project Survivor 2D. A clean architecture starts from the folder structure. Create these folders: scripts, player, core, weapons, enemies, sprites, prefabs, scriptable objects. This will keep everything clean and scalable as the game grows. Before we start coding, let's import our real player artwork so we can work directly with the final visuals. Inside the folder named Sprites, drag and drop your player sprite sheet into Unity. Now click on the sprite sheet, and in the inspector, we need to configure it properly for Pixel Perfect 2D. First, set sprite mode to multiple. Set filter mode to point, no filter. This avoids blur on pixel art. Set compression format to RGBA 32-bit for maximum quality. Now click on Sprite Editor. Inside the Sprite Editor, we will slice the sheet. Now, Unity automatically splits your sprite sheet into all the animation frames we need for our player. Perfect. Our player artwork is ready to use. Now that our player sprite sheet is sliced, let's create our very first animation, the idle animation. Inside the sprites folder, find the 2 frames that belong to the idle pose. Select both frames, just hold Shift and click on each one. With both selected, drag them directly into the scene or into the player object in the hierarchy. Unity will automatically open the Save dialog for creating an animation. Let's name it player_idle and save it inside a new folder called Animations. Unity also created an animator controller for us. Let's keep that and rename it to Player Animator. Now press play, and you can see the player breathing or blinking depending on the artwork. This is our first animation finished. Clean, simple, and ready to connect to movement later. Now let's create the walking animation for our player. Just like we did for the idle animation, we'll use the real sprites directly from our sliced sheet. Inside the sprites folder, select all the frames that belong to the walk cycle. In my case, I have 6 frames, but it doesn't matter if it's 2, 4, or more. Just select all the walk sprites together. Once the walk frames are selected, drag them into the scene or onto the player object. Unity will again open a window, asking to save a new animation. Let's name this animation player_walk and save it inside our animations folder. That's it. The walking animation is created. You should now see 2 animations in your project: player_idle and player_walk. In the next step, we'll set up the animator transitions so the player switches between idle and walking automatically depending on movement. Now let's finish the animator setup. Because our character uses only left and right movement animations, we only need one parameter: horizontal. We don't need any animation change for the y-axis, so the animator stays very simple. Open the animator window. You should see the idle and walk animations. Let's add one parameter: a float named horizontal. Now we create transitions. For the idle walk transition, we want the walking animation to play anytime the player is moving left or right. For the walk idle transition, we only want to return to idle when the player fully stops moving horizontally. So add the condition, horizontal equal to 0. Finally, we flip the player sprite in code whenever horizontal is negative. Now the character idles when not moving, walks when moving left or right, and flips depending on the direction. Clean and simple. Now let's create the actual movement script that controls our player and also drives the animator parameters we just created. Inside the scripts folder, create a new script called player movement and add it to the player object. First, I'll import Unity Engine and then create the base structure of the class. I'm adding require component attributes to make sure the player always has a rigid body 2D, an animator, and a sprite renderer. This keeps everything clean and avoids missing component errors. Now I'll declare a public movement speed and private references for the Rigid Body 2D, Animator and Sprite Renderer. I also create a Vector2 that will store the movement input. Inside Awake, I'll cache all the components. This is faster and cleaner than calling getComponent every frame. In Update, I read the horizontal and vertical inputs. We'll use vertical only for movement, not for animations, since our character only uses left and right animation states. Now I'm sending the absolute value of the horizontal input to the animator under the parameter horizontal. This matches the transitions we set earlier. If horizontal is greater than 0, we play walk. If it's close to 0, we play run, we return to idle. And finally, I'll flip the sprite depending on the direction. If we move left, flip X is true. If we move right, flip X is false. Finally, in Fixed Update, I move the rigid body using Move Position, which is the recommended way of moving physics objects in Unity. This gives us smooth, clean, and stable movement. And that's it. Let's go back to Unity, let's add a Sprite 2D as a background and test it. When I press play, the character idles when not moving, plays the walk animation when moving left or right, and flips correctly depending on direction. But we still have a little problem. The player is falling because of the Rigid Body 2D. Let's fix it. If your player is falling down, that's because the Rigid Body 2D still has gravity enabled. Since this is a top-down game, we don't need gravity at all. So let's select the player, go to the Rigid Body 2D component and set gravity scale to 0. Now the player will stay perfectly still unless we move it with inputs. Let's go back and test it. The movement is clean, responsive, and ready to be expanded later. Movement is done. Next, we're going to add player attacks, weapons, enemy spawning, and full wave systems. This is where the game really starts to come alive. If you're excited for the next episodes, make sure to subscribe and hit that like button. You won't want to miss what's coming next. Welcome back everyone to episode 2 of our Unity 2D Survivors series. In this episode, we're going to create the full shooting system. Automatic firing, bullets, damage, and everything we need for weapons in this game. Let's jump right in. First, we need a bullet. Inside the sprites folder, I'll select a small projectile sprite. Anything round or bright works for testing. Drag it into the scene, rename it to Bullet, and let's add a Rigid Body 2D and a Circle Collider 2D. Make the Rigid Body kinematic and the collider a trigger. Then I'll create a Scripts, Weapons folder, and add a new script called Kunai. Let's open it. Now, let's create the player shooting script that will handle automatic firing. Inside Scripts, Weapons, I'll create a new script called Player Shooting. I'll start by importing Unity Engine and creating the base structure for the Kunai class. This script will be responsible for moving the projectile forward and destroying it after a short time. Next, I'll add a speed, a lifetime, and a direction. Speed controls how fast the kunai travels, lifetime will automatically destroy it after a few seconds, and direction is where the kunai should move, left or right, depending on the player. In the start method, I'll destroy the kunai after its lifetime expires. This keeps the scene clean and prevents hundreds of unused projectiles from staying in memory. And in Update, I'll move the kunai using Translate. Multiply by speed and delta time, so it moves smoothly and consistently each frame. This makes the kunai fly in whatever direction we set when we spawn it. And that's our kunai projectile script. It moves in the given direction, destroys itself after a short time, and stays lightweight and clean. Now we can spawn this kunai from the player and change its direction depending on whether the player is facing left or right. Now that our kunai projectile is ready, let's create the script responsible for shooting it from the player. Inside the Scripts folder, I'll create a new script called Player Shooting. Let's open it. First, I'll add a reference to our kunai prefab so the player can spawn it. Then I'll add a fire rate to control how often the player shoots and a fire cooldown to track the timing between shots. I'll also get the sprite renderer so we can check if the player is flipped. This will tell us whether to shoot left or right. Inside Start, I'll cache the sprite renderer. We already used this in the movement script, and we'll reuse it to determine the shooting direction. In Update, I'll decrease the cooldown every frame. If the cooldown reaches 0 or below, that means it's time to shoot again. So we call the shoot method and reset the cooldown to the fire rate. Now let's write the actual shoot method. First, we'll check the facing direction of the player. If the sprite is flipped, the player is facing left. Otherwise, right. Then we instantiate a new kunai at the player's position. Finally, we assign a direction to the kunai. Positive X for right, negative X for left. This is all we need for a simple automatic shooting system. Alright, let's go back into Unity and test our shooting system. When I press play, you can see the player automatically throwing kunai at a steady rate. If I move to the left, the kunai flip and fire to the left. If I move right, they fire to the right. Everything is working smoothly. Exactly like a Survivors.io style auto attack. This is a great foundation for the weapon system we'll be expanding later with damage upgrades, weapon variations, multiple projectiles, and more. If you're enjoying this series and you want to see the next episodes, enemy spawning, waves, upgrades, boss fights, make sure to subscribe to the channel, hit the like button, and turn on notifications so you don't miss the next tutorials. Right now, our player can only fire kunai left and right, because the shooting direction is based on whether the sprite is flipped. But in a real Survivors or Vampire Survivors style game, we want the player to be able to shoot in all directions, up, down, left, right, and diagonally down, diagonally, and anywhere on the 360 circle. So let's upgrade our shooting system to do exactly that. The easiest and cleanest way to do this is to use the movement direction of the player. If the player is moving up, they shoot up. If they move down, they shoot down. If they move diagonally, the kunai will also fire diagonally. We'll start by adding a new variable inside our player movement script to store the last movement direction. Anytime the player presses a movement key, we save the direction they are moving in. And if the player stops moving, we keep the last known direction, so the player still shoots even when standing still. Now in the player shooting script, instead of checking if the sprite is flipped, we grab the movement direction from the player movement script. If the last direction is 0, meaning the player hasn't moved yet, we'll just default to firing to the right. With this change, our kunai can now fire in every direction depending on where the player is moving. Let's test it. If I move up, the kunai goes straight up. If I move down, it shoots down. Left and right still work. And diagonal movement creates diagonal shots, just like in a real Survivors.io style game. This adds a lot more dynamism to the gameplay and makes the combat feel much more alive. Now that our player can shoot in 360 degrees, it's time to bring some life into the scene. Let's create our very first enemy. Inside the hierarchy, I'll right-click, go to 2D Object, Sprite, and choose a simple shape. For now, a square or circle is perfectly fine as a placeholder. I'll rename this object to Enemy, because this will be our base enemy that we'll build on in the next episodes. Before we move forward, we need to give this enemy a new tag so our scripts can find it later. So with the enemy selected, I'll go to the top of the inspector where it says Tag, click it, and choose Add Tag. I'll create a new tag called Enemy. all uppercase or lowercase doesn't matter, as long as you're consistent. Now I select the enemy object again, open the tag dropdown, and assign it the new enemy tag. Perfect. We now have a basic enemy object in the scene, and it's tagged correctly so our shooting system and upcoming enemy logic can detect it. Right now, our player shoots all the time, but that's not how Survivors.io works. We only want the player to shoot when an enemy is nearby, so let's add a detection radius around the player. First, I'll create a new variable called detection radius. This will control how close an enemy needs to be for the player to fire a kunai. Next, I'm updating the getNearestEnemy function. Instead of scanning the entire map, I limit the search to only enemies that are within this radius. If no enemy is close enough, the function simply returns null. Now, inside update, before the player shoots, I check. Is there an enemy inside my radius? If not, the player just waits. If yes, the attack activates automatically. And that's it. The player now reacts only when danger is near. Let's test it. If I bring an enemy close to the player, the kunai starts firing. If the enemy moves out of range, the shooting stops. This feels a lot more polished and much closer to real Survivors.io behavior. Right now, our kunai shoots in the correct direction, but it's not smart. It doesn't actually focus on enemies like in Survivors.io. So let's upgrade it and turn it into a real homing kunai. First, when we spawn a kunai, we look for the nearest enemy and give that enemy as the kunai's target. Then inside the kunai script, instead of just flying forward, the kunai constantly recalculates its direction toward the target. We smoothly rotate the kunai using Quaternion Rotate Towards, and then move it forward in the direction it's facing. This means the kunai now tracks the enemy in real time. If the enemy moves, the kunai turns and follows it. Let's press play. Perfect. The kunai now intelligently focuses on enemies, rotates toward them, and chases them just like a guided projectile in Survivors.io. Much better than before. Now that the kunai can follow the enemy, we want it to disappear when it actually hits the target. To do that, I'll add an onTriggerEnter 2D function. If the kunai collides with something tagged as enemy, we simply destroy the kunai. Make sure the kunai has a Collider 2D set to trigger, and the enemy has a normal Collider 2D. And that's it. Let's test it. When the kunai touches the enemy, perfect, it gets destroyed immediately. This makes the weapon system feel much more responsive and polished. Our kunai is rotating toward the enemy, but the head still doesn't visually touch the target. This happens because the sprite isn't aligned with Unity's default forward direction. Unity expects projectiles to point to the right, but my kunai sprite was drawn pointing up. So even though the rotation is correct mathematically, visually it looks wrong. To fix this, I simply open the kunai prefab and rotate the sprite renderer so that the kunai points to the right at rotation 0. Now, when the script rotates the kunai and moves it forward using space.self, the head of the kunai correctly faces the enemy and hits them perfectly. Let's test it. Perfect. Now the kunai head touches the enemy exactly as it should. If you're enjoying this series and you're learning something new, make sure to subscribe to the channel. There's a lot more coming. Enemies, waves, upgrades, boss fights, and full Survivors.io gameplay. So hit that subscribe button, drop a like, and let's keep building this game together. Now that our player, movement, and shooting systems are working, it's time to start building the environment. In this part, we're going to set up the world using Unity's tile map system, beginning with a simple grass ground. Tile maps are perfect for top-down Survivors.io style games because they let us build large, seamless environments without placing hundreds of individual sprites. Let's get started. First, in the hierarchy, I'll right-click and go to 2D Object, Tile Map, Rectangular. Unity automatically creates a grid parent and a tile map child. I'll rename the tile map to Ground because this will be our main layer for the grass. Next, I'll import my grass tile sprite into a folder called Tiles. Make sure the sprite is set to Filter Mode, Point, No Filter, Compression, None, Pixels per Unit, whatever matches your art. With the tile map selected, I'll open the Tile Palette window by going to Window, 2D, Tile Palette. I'll create a new palette called Environment. Then I simply drag the grass tile into the palette. Now with the brush tool selected, I can start painting the ground directly in the scene view. Let's paint a big area of grass so our player has space to walk around. Before we continue building the environment, there's a small visual issue we need to fix. You might notice that the tiles in the scene view don't look perfectly rendered. This usually happens because the sprite's pixel size, or pixels per unit, doesn't match the scale of our tile map. So let's fix it. I'll select the grass tile sprite in the project window, and in the inspector, I'm going to adjust the pixels per unit value so it matches the resolution of the artwork. In my case, I'll change it to 64, then I'll click Apply. This is an important step because in games like Survivors.io, visual clarity is everything. Clean tiles mean smoother movement, better readability, and a more professional environment. All right, with that fixed, let's continue building our level. And that's it. We now have a clean, solid grass ground made with tile maps. This gives us a real environment to test movement, shooting, and enemies. And it will be the base for adding details like paths, obstacles, decorations, and props in future videos. Welcome back to the series. In this video, we're finally going to start working on our enemy. Up until now, we've been focusing on the player, movement, shooting, tile maps, and basic environment setup. But the game will only come alive when we add enemies that move, animate, and react to the player. So let's set up our first enemy step by step. First, I'll select the enemy sprite sheet and open it in the sprite editor. Just like we did with the player, I'll slice the sprites and then create the enemy's idle and walk animations. Alright, now let's set up our enemy's animation. For this episode, we're only working on the walking animation, since our enemy will constantly walk toward the player. First, I'll select the enemy sprite sheet in the project window. Then, I'll drag the sprite directly into the scene to create a new game object. I'll rename this object to Warrior. This will be our base enemy for the rest of the series. Now, with the Warrior selected, I'll open the sprite editor if needed and make sure the sprite is sliced correctly. Once everything looks good, let's create the walking animation. I'll select all the walk cycle frames in the project window, then simply drag them into the animator window or into the scene. Unity automatically creates an animation file. I'll name it enemy_walk. This gives us a looping walking animation that we'll use when the enemy chases the player. Let's test it quickly. Perfect. The warrior is now walking, and we're ready to continue setting up the enemy's movement and collision. Now that our warrior enemy has its walking animation, let's set up the collider so it can properly interact with the player and our kunai projectiles. With the warrior selected in the hierarchy, I'll go to the inspector and click Add Component, Box Collider 2D. You can also choose Circle Collider 2D depending on the shape of your enemy. But in this case, a box collider works well. I'll adjust the collider so it fits nicely around the character's body. It doesn't need to be perfect. Just make sure it covers the main shape of the sprite without extending too far beyond it. This collider will be used for detecting hits, collisions, and later for applying damage. And that's it. Our warrior now has a proper collision area, which means our kunai will soon be able to detect it and react on impact. Now that our warrior enemy has a collider, the next step is to add a rigid body 2D, which allows Unity's physics system to track movement and collisions properly. With the warrior selected, I'll go to the inspector and click Add Component, Rigid Body 2D. By default, Rigid Body 2D is set up for platformers, so we need to make a few adjustments. First, I'll set Body Type to Dynamic. This allows the enemy to move and receive physics events, like trigger collisions with our kunai. Next, because this is a top-down game and not a side-scrolling platformer, we don't want gravity at all, so I'll set gravity scale to 0. And finally, I'll freeze the rotation on the Z-axis. This prevents the enemy from spinning around if it bumps into something or collides with other objects. Now the warrior is fully prepared for top-down movement. It can collide, trigger events, and interact with the environment exactly the way we want. Before we start adding more enemies, we need to think about the architecture of our game. Most enemies in Survivors.io behave almost exactly the same way. They chase the player, they collide with the player to deal damage, and they don't use complex attack animations. Since all these enemies share the same core behavior, it would be a waste of time to write the same movement and damage code over and over again. So instead, we're going to create a parent enemy class, a base script that handles all the common logic. Then, every enemy we add to the game will simply inherit from this class. This gives us clean, scalable, and maintainable code. If we want to tweak enemy behavior later, we change it in one place, and all enemies automatically update. Let's create the enemy base script now. Now, let's create a simple base class for all our enemies. Most enemies in this game will behave the same way. They move toward the player and deal damage on collision. So instead of repeating this code for every enemy, we'll put it all in one common script. Inside Start, I grab a reference to the player using the player tag. Then, in Update, I calculate the direction from the enemy to the player and move the enemy forward using a simple normalized vector. Finally, I'll add an on-trigger into 2D method so later we can handle damage when the enemy touches the player. This base script will be the foundation for all enemy types we create next. Now I'm creating the warrior enemy script, and instead of writing new movement or collision code, I simply make it inherit from the enemy base class. This means the warrior automatically gets all the base behaviors: movement, collisions, and eventually health and damage. If we want to create new enemy types later, for example, a fast enemy, a tank enemy, or a ranged enemy, we simply create new scripts that inherit from enemy base and override only the parts we want to change. This gives us a clean and scalable architecture that will support dozens of enemy types without duplicating code. Now that our enemy base script is ready, let's apply it to our warrior enemy. I'll select the warrior in the hierarchy, and I'm going to add a new component called warrior enemy. Since warrior enemy inherits from enemy base, the the warrior now automatically gains movement and collision behavior. Next, we need to make sure Unity recognizes this object as an enemy. So with the warrior still selected, I'll go to the top of the inspector and change its tag to enemy. And while we're setting up tags, let's also tag the player. I'll click on the player object and assign it the player tag. This is important because our enemy-based script looks for the player tag to know who to chase. Perfect. Now the warrior enemy knows who the player is, and the player is correctly identified in the scene. Alright, now that our warrior enemy has the movement script, the collider, the rigid body, and the correct tags, let's go ahead and test everything. I'll hit play, and there we go. The warrior is now chasing the player around the map exactly as expected. The movement looks smooth, the enemy follows the direction of the player, and our base system is working great. But we still have one small problem. Even though the warrior moves toward the player, he does not actually face the player. The sprite keeps its default orientation instead of turning left or right, depending on the direction it's walking. This looks a bit unnatural, and we definitely want the enemy to face the player while chasing, just like the player flips based on their movement. So in the next step, we're going to fix this and make the warrior rotate or flip correctly depending on where the player is. Let's take care of that now. To fix this, all we have to do is compare the enemy's position to the player's position and flip the sprite depending on which side the player is on. If the player is to the right of the warrior, we'll make the sprite face right. If the player is to the left, we flip it so the warrior faces left. This gives us a simple and clean 2D facing system, and it makes the chase animation look much more natural. Alright, let's test the fix and see if our warrior enemy is now facing the player correctly. I'll hit play. And now, as the enemy chases the player, you can see the sprite flipping left and right depending on where the player is. If I move to the right, the warrior turns to the right. If I move to the left, the warrior flips and faces me immediately. This looks much more natural and makes the enemy feel alive instead of sliding around the map. So our facing direction fix is working perfectly. And that's it for this part. Our warrior enemy now walks, chases the player, and faces the correct direction while moving. Everything is working smoothly. If you enjoyed this tutorial and want to follow the full Survivors IO series step by step, don't forget to like the video and subscribe to the channel. It really helps the series grow, and you won't miss the next episodes where we add enemy health, damage, death effects, spawners, and waves. Thanks for watching, and I'll see you in the next one. Now that our warrior enemy can move and face the player correctly, let's give him a simple health system. For now, the health won't be displayed on screen. We just want the enemy to take damage and be destroyed when it reaches 0. So I'm going to create a new script called Enemy Health. Inside this script, I'll give the warrior a starting health of 50, and our kunai will deal 25 damage on hit. That means it takes exactly 2 kunai hits to defeat the enemy. Let's write the code. I'll add a simple take damage function that reduces the enemy's health. If the health reaches 0 or below, we call a die function and destroy the enemy object. This keeps everything clean and modular. Other enemies can reuse this health system simply by changing the max health value. Now inside the kunai script, when the kunai collides with an enemy, I call take damage 25 to apply the damage. Then I destroy the kunai immediately so it doesn't pass through the enemy. With this setup, one kunai hit deals 25 damage, and since the warrior has 50 health, it will take exactly 2 hits to kill him. Before we test the damage system, we need to make sure our warrior actually has the new enemy health script attached. So I'll select the warrior object in the hierarchy, click Add Component, and add the enemy health script we just created. By default, the warrior now starts with 50 health, which matches what we set in the script. Alright, with that in place, we're ready to run the test. The warrior chases the player, and when the kunai hits him, he takes damage. After 2 hits, his health reaches 0, and the enemy gets destroyed. Perfect. Our health and damage system is working exactly as expected. Before we move on, Let's add a tiny improvement. Right now, when the warrior gets hit, he doesn't react at all. He just keeps walking. To make the impact feel better, we're going to add a very small recoil effect. Nothing big, nothing dramatic. Just a little push backward when the kunai hits. This makes the hit feel more responsive and gives the enemy a bit more life. Before we test, let's set the fire rate to 3. It means our player will fire once every 3 seconds. Alright, let's test the recoil effect we just added. I'll hit play. And now, when the kunai hits the warrior, you can see he gets pushed back just a little bit. It's subtle, but exactly what we want. A small recoil that makes the hit feel more impactful without breaking the movement. The enemy still chases the player normally, but each time he gets hit, he reacts with a quick, natural-looking bump backward. This already makes the gameplay feel much smoother and more polished. In this part, we're going to add a classic hit effect used in almost every 2D action game. A quick white flash when the enemy gets hit. This simple effect makes combat feel more responsive, more satisfying, and much more professional. So today, we'll implement a clean flash system that activates every time our warrior enemy takes damage. To create our flash effect, we first need a special material that we can swap onto the enemy when he takes damage. So let's start by creating a new folder. I'll right-click in the project window, choose Create, Folder, and name it Materials to keep everything organized. Inside this folder, I'll right-click again and create a new material. I'll name it On Damage Flash. Now with the material selected, I'll go to the inspector, open the shader drop-down, and change it to GUI, Text Shader. This shader lets us force the sprite to appear fully white when applied, which is perfect for our hit flash effect. Next, let's create a script that will manage the visual effects for any entity in the game, like enemies, or even the player later on. I'll right-click in the Scripts folder and create a new Sears script called Entity_VFX. Inside this script, we'll make references to our sprite renderer and the flash material. So I'll add 2 serialized fields. One for OnDamageVFX Matte, which is the flash material, and one float called OnDamageVFX Duration, which I'll set to 0.15 seconds. This will control how long the flash effect lasts. Now let's set up the logic that will actually trigger the flash effect. Inside the Entity VFX script, I'll start by going into the Awake method. Here, I want to grab the sprite renderer from the enemy, so I'll use getComponentInChildren sprite renderer, which ensures we get the renderer even if it's on a child object. Next, I'll store the enemy's original material by assigning sprite renderer.material to a new variable called OriginalMatte. This is important because after flashing white, we want to return the sprite to its normal material. Now let's create the coroutine that performs the flash. I'll make a new IEnumerator called OnDamageFlashCo. Inside this coroutine, the first thing we do is swap the sprite's material to OnDamageVFX Matte, which is our white flash material. Then we wait for a very short amount of time, the flash duration, by using YieldReturnNew WaitForSeconds OnDamageVFX Duration. Later, we'll restore the material back to the original one, but for now, we just set up the structure. This coroutine will give us a clean, smooth flash effect every time the enemy takes damage. Now we want the flash effect to play every time the enemy takes damage. To handle this properly, we need a method that starts our flash coroutine, but also stops it if it's already running. I'll first create a new coroutine variable called onDamageVFXCo. This will store a reference to the flash coroutine whenever it's active. Next, I'll create a public method called playOnDamageVFX. This is the method we'll call from other scripts, like enemy health, whenever the enemy gets hit. Inside this method, the first thing we'll do is check if the coroutine is already running. If onDamageVFXCo is not null, that means a flash is already active, so we stop it using stopCoroutine. Then we start a brand new coroutine and store the reference in onDamageVFXCo. This makes sure the flash effect always restarts cleanly, even if the enemy is hit multiple times very quickly. Now that our flash system is ready, we need to connect it to the enemy's health so the flash effect plays every time the enemy takes damage. Inside the enemy health script, I'll start by creating a new reference to our EntityVFX component. I'll call it EntityVFX. Then, inside the start method, I'll grab that component using getComponentEntityVFX. This gives the health script access to the visual effects system. Now inside the takeDamage method, right after we reduce the enemy's health, we simply call our method. This ensures the flash effect triggers every single time the enemy receives damage. Before we test, we need to make sure the warrior actually has the EntityVFX script attached. So I'll select the warrior enemy in the inspector, add the EntityVFX component, and assign the material we created earlier, the onDamage flash material. Once that's done, the enemy is fully wired up and ready to flash when hit. And before testing, let's delete the 2 instance of the warrior and create a prefab. I'll hit play. And there we go. When the enemy gets hit, the white flash appears for a moment and then cleanly returns to the original material. This is exactly what we wanted. A quick, sharp feedback effect that makes hits feel impactful, but without permanently changing the enemy's appearance. The recoil works, the damage works, and now the flash effect works perfectly as well. Everything is looking great, and we can move on to the next feature. If you're enjoying the series so far, make sure to like the video and subscribe for more Unity tutorials. It really helps the channel grow. Before we start adding XP and leveling, we need to think about the future of our game. Later on, we want to add a full skill tree, equipment, stat upgrades, and passive bonuses. So we need an XP system that is clean and scalable. So instead of just throwing variables everywhere, we're going to build a simple architecture that we can easily expand in future episodes. We'll create a player stats system that will store all the characters' values like health, speed, attack, and anything we add later. Then we'll create a separate XP and leveling system whose only job is to track experience points, calculate level ups, and notify the rest of the game when the player levels up. Finally, we'll keep everything modular. So when we get to skill trees or equipment, we can plug them right in without rewriting anything. Let's set up the structure now. Now I'm creating the player XP script. This script keeps track of our current XP, the XP needed for the next level, and the player's current level. In the addXP method, I increase the XP and check if we reached the next threshold. If we did, we call level up, increase the XP requirement, and trigger an event that other systems will listen to later, like a skill tree or a level up UI. This makes the system clean and expandable without changing the core code in the future. Let's test the XP system. I'll hit play, destroy a few enemies, and you can see the XP increasing. Once we reach the threshold, the player levels up and the XP required for the next level increases. Everything works smoothly, and the system is fully expandable for the future skill tree and equipment system. Now that we have our leveling system working behind the scenes, it's time to display it on screen with a proper XP bar, just like the one in Survivors IO. The XP bar will fill up every time we gain experience, and when it reaches the maximum, it resets and shows the next level. I'll start by creating a new canvas for the HUD, then inside it I'll add an image for the XP bar background. Next, I'll duplicate it to create the fill image, make it a child of the background, and change its image type to filled. Setting the fill method to horizontal lets the bar smoothly fill from left to right when the player gains XP. Now that the visual part is ready, let's connect it to the XP system. Now I'll create a small script called Player XPUI. This script simply reads the current XP and the XP needed for the next level, and updates the fill amount of the bar. So if we have, for example, 20 XP out of 50, the bar will automatically fill to 40%. I'll assign the XP fill image in the inspector, link the Player XP component, and the bar will update automatically as we play. I'll hit play. And now every time I defeat an enemy, the XP bar begins to fill. When it reaches the max value, we level up, and the bar resets and continues filling for the next level. This matches the behavior from Survivors IO and gives us a clean, responsive XP display on screen. Now that the XP bar is working, let's add a simple UI element to display the player's current level. Just like in Survivors IO, we want a small text label showing Level 1, Level 2, and so on. Whenever the player levels up, this text should update automatically. Let's set that up. Now I'll create a player-level UI script. This script listens to the level up event from the XP system and updates the text automatically. Whenever the player levels up, we'll simply refresh the label to show the new level number. This keeps everything modular and clean. No duplicated code. Let's test the level display. I'll hit play. When we kill enemies, the XP bar fills. And as soon as we reach the next level threshold, perfect. The text updates from level 1 to level 2. Every time we level up, the label changes instantly. It's clean, simple, and matches exactly how Survivors.io displays player level. Now that our XP bar and leveling system are working, it's time to add XP orbs. Just like the green crystals you pick up in Survivors IO. Every time an enemy dies, there should be a chance for a small or a big orb to drop. Small orbs give a little XP, big orbs give more. This makes progression more rewarding and visually clear. Let's set up the XP orb system now. In this part, we're going to create the big XP orb, which is the crystal dropped when an enemy dies. This orb gives the player more experience than the small one, and it's the main reward for defeating enemies. Let's start by creating the big orb prefab. Drag the orb sprite into the scene, rename it. Green XP orb. Big. Add a circle collider 2D and set is trigger to true. Now I'll attach a script that handles the XP value of the orb and how the player collects it. When the player touches the crystal, we'll add XP to the XP system and destroy the orb. Next, we need to tell the enemy to drop this big orb when he dies. I'll go into the enemy health script and add a reference to the big orb prefab, then instantiate it at the enemy's position when he dies. Let's test the big XP orb. I'll hit play, defeat an enemy, and you can see that every time one dies, it drops a large green crystal. When the player touches it, the orb disappears and the XP bar increases. This works perfectly, and now we have our core XP reward system in place. Right now, our big XP orb drops every time an enemy dies. But we want it to be random so the player doesn't get a guaranteed reward from every kill. So let's add a simple drop chance system. We'll create a percentage value, and when the enemy dies, we'll roll a random number. If the number is below our drop chance, the orb spawns. Otherwise, nothing drops. This gives us the same behavior seen in Survivors IO. Sometimes enemies drop a crystal, sometimes they don't. Let's test the new random drop system. I'll hit play and defeat a few enemies. You can see that sometimes the big crystal drops and sometimes nothing drops at all. That's exactly what we want. A chance-based XP reward system that keeps combat more dynamic and unpredictable. Now we're going to create the small XP orb, which naturally spawns on the map for the player to collect. Unlike the big orb that drops from enemies, the small one appears randomly around the map at intervals. This helps the player gain XP even when there aren't many enemies around and keeps the environment feeling alive. Let's start by creating the small orb prefab. Now we need a system that spawns small XP orbs around the map at random positions. We'll create a simple spawner that generates orbs every few seconds, inside a defined area or radius. Later on, we can make this smarter with biome zones or spawn waves, but for now, we'll keep it simple. Now let's create an empty game object and call it XPorb Spawner. Place the spawner at the center of your map and add a component XPorb Spawner. Assign the small orby prefab. Add a new tag XPorb Small and assign it to the Small Orb prefab. I'll press play, and every few seconds you can see new small XP crystals appearing around the map. When the player walks into them, they get collected and the XP bar increases. If the number of orbs reaches the maximum limit, the spawner stops automatically, preventing performance issues. This gives our map some life and lets the player gain XP even when enemies are not nearby. Now it's time to add the magnet effect, the ability for nearby XP orbs to fly toward the player. But instead of hard-coding anything, we're going to build a clean, scalable system. Magnet range will later be something we can upgrade through items, boosts, or level up choices. So let's create a dedicated magnet component for the player that detects orbs within a radius and pulls them in. Inside the player magnet script, I'll add a magnet radius that defines how far the player can attract XP orbs. In the update method, I call pull nearby orbs. This uses physics 2D overlap circle to detect all objects inside the magnet radius. If the object is a small or big XP orb, we gently move it toward the player using move towards. This keeps the system simple, modular, and fully upgradable later. I'll hit play. And as the player walks near XP crystals, you can see them being pulled toward the player automatically. This feels really smooth and makes the gameplay much more satisfying. And the best part is that this system is fully scalable. We can increase the magnet radius later using items, upgrades, or level up choices without rewriting anything. In today's video, we're adding a new enemy type, the Lancer. This enemy works just like the warrior. He chases the player and deals contact damage. But he has different stats, specifically lower health and slightly faster movement. This helps us diversify enemies without rewriting behaviors, keeping everything scalable. Let's start by adding the sprite sheet. First, I'll drag the Lancer sprite sheet into our sprites folder. With the sprite selected, I'll go to the inspector and set sprite mode, multiple, filter mode, point no filter, compression format, RGBA 32-bit. Then I'll click Sprite Editor, slice the sheet using the automatic slicer and hit apply. Now we have all the frames we need for the running animation. Next, I'll create the Lancer's running animation. I'll select all the running frames, drag them into the scene, and Unity will ask to create a new animation. I'll name it Lancer_run and save it in our animations folder. The animation is now ready, so let's build the enemy object. Now I'll rename the object to Lancer and assign a tag of enemy. Then, just like with our warrior enemy, I'll add a sprite renderer, a rigid body 2D set to dynamic, a circle collider 2D for collision detection, the enemy-based script for movement and chasing behavior, and finally, the enemy health script. This gives the Lancer all the basic logic our enemies share. Now let's give the Lancer unique stats. Inside the enemy health component, I'll reduce his max health. For example, from 50 down to 25. So he dies faster than the warrior. Everything else stays the same. He chases the player, gets knocked back on hit, flashes when damaged, and drops XP orbs with the same drop system. Let's hit play and test the Lancer. As you can see, he spawns correctly, plays his running animation and chases the player using the same enemy movement logic. He has less health than the warrior, so he dies quicker, the hit flash works, and the XP orbs behave exactly as expected. Our new enemy is now fully integrated into the game, and the system remains clean, scalable, and easy to expand with. In this part, we're adding a brand new enemy type, the Monk. Just like we did in the previous tutorial with the Lancer, we're going to import the Monk sprite sheet, create his running animation, set up his colliders and scripts, and give him unique stats. The Monk behaves exactly like the other enemies. He chases the player and deals contact damage. But he's much slower and has a lot more health, making him a tank-type enemy. Let's get started. I'll begin by dragging the Monk sprite sheet into our sprites folder. With the sprite selected, I'll set Sprite Mode, Multiple, Filter Mode, Point, No Filter, Format, RGBA, 32-bit. Then I'll open the sprite editor, slice the sheet, and click Apply. Next, I'll select all the Monk running frames, drag them into the scene, and Unity will prompt me to create an animation. I'll call it monk_run and save it inside the animations folder. Now I'll rename the object to Monk, assign the enemy tag, and add the core components: Rigid Body 2D, Dynamic, Collider, Enemy Base Script for movement, Enemy Health Script for stats, Worry Roar Enemy, Entity VFX for flash effect. This gives the Monk the same behavior as our other enemies, so we can reuse all our existing systems. Inside enemy health, I'll increase his health, for example, from 50 to 100, and in enemy base, I'll slightly reduce his movement speed to make him slower and heavier. Now, we have a tank-style enemy that takes longer to kill but moves slower than the others. Let's hit play and test the Monk. He chases the player, takes more hits before dying, plays his running animation, and drops XP orbs exactly like our other enemies. And that's it. Our Monk enemy is now fully integrated using the same scalable architecture as the Warrior and the Lancer. In this part, we're adding two very important gameplay elements: a game timer that tracks how long the player survives, and a kill counter that displays how many enemies the player has defeated. These are simple features, but they make the game feel much more complete, and they help us build wave systems and difficulty scaling later. Let's start by creating the UI. Inside HUD Canvas, right-click UI Text. Rename Timer Text, default value 0. To keep our project scalable and clean, we're going to create a game manager that tracks all global gameplay values, like the timer and the total number of kills. This avoids putting logic in random scripts and prepares our system for waves, difficulty scaling, and boss fights later. Instead of updating the UI manually, we'll make two small UI scripts that automatically refresh themselves using the Game Manager values. This keeps the UI clean, lightweight, and independent from gameplay code. Now, we need to notify the Game Manager every time an enemy dies. So inside Enemy Health, we'll call Register Kill when the enemy is destroyed. Let's test everything. I'll press play. The timer starts automatically from 0. Every time I kill an enemy, the kill counter increases. Everything updates instantly and cleanly. This now opens the door for wave systems, boss timers, and difficulty scaling in future episodes. In today's tutorial, we're going to add one of the most essential features for any top-down game, a camera follow system. Right now, our player moves around the map, but the camera stays still. This makes it hard to see where we're going and breaks the gameplay experience. So let's set up a smooth camera follow script that keeps the player centered and gives us a clean Survivor's IO feel. Let's start by creating a new script called Camera Follow. This script will take the player as a target, follow their position, and optionally add some smoothing so the movement feels more polished. Now I'll select the main camera and attach the camera follow script. Then I'll drag the player into the target slot. To keep the camera from snapping too close, I'll add a small offset of x equals 0, y equals 0, z equals -10. This keeps the camera at the right zoom level while still following the player smoothly. Let's test it. When the player moves, the camera now follows perfectly, and the smoothing makes the movement feel much more professional. This gives us that clean Survivor's IO style where the player is always centered and the world moves around them. Now our gameplay is much easier to control and far more enjoyable. In this part, we're finally adding one of the most important systems in a Survivor's IO style game, the enemy spawner. Up until now, we've been placing enemies manually in the scene, but for a real survival game, enemies must spawn automatically, continuously, and from all directions. So today, we're creating a clean, scalable spawner that generates enemies around the player at a fixed interval. Later on, this system will evolve into enemy waves, boss waves, elite enemies, and difficulty scaling. But for now, let's get the core spawner working. Let's begin by creating an empty game object in the hierarchy, and we'll call it Enemy Spawner. This object will control when and where enemies appear. Inside the spawner, we check the timer. Whenever the timer reaches the spawn interval, we call Spawn Enemy. To spawn enemies around the player, I use a random direction and multiply it by the spawn radius. This means enemies always appear outside of the camera view and walk toward the player, just like Survivors.io. And because the spawner takes an array of enemy prefabs, we can easily add more enemy types later. Fast enemies, tank enemies, ranged enemies, anything. Now we just need to hook it up in the inspector. I'll select the enemy spawner object, drag the player into the player field, and drag all enemy prefabs into the enemy prefabs list. Warrior, Lancer, Monk, and any future enemies we add. And that's it. The spawner is now ready to run. Let's test it. I'll press play, and every few seconds, enemies start appearing around the player. They spawn outside the camera, walk toward the player using their AI, and everything works perfectly. We now have an automatic enemy generator, and this is the foundation for building real survival gameplay.